Okay. So, we start with steady state spectroscopy. What is the meaning of steady state spectroscopy? Those who have used this would know that it essentially means that we are recording spectra, but why is recording spectra called steady state? To do that, again we go back to something we learned in class 11. What is the meaning of steady state? What is the difference between equilibrium and steady state? Open system. Steady state means you don't see an apparent change, but the system is open. Equilibrium happens in a closed system. So, for the sake of simplicity, let us consider a molecule with two energy levels, lower one and a higher one. Okay. You shine it with light, that causes some upward transition. This is called absorption. Okay. And then this molecule comes back to the ground state as well, either by a radiative pathway or by a non-radiative pathway. Well, the names are self-explanatory, but tell me what is the meaning of radiative pathway, what is the meaning of non-radiative pathway? Yeah? Radiative pathway means light is emitted, non-radiative pathway means light is not emitted. So, molecule comes down from excited state to ground state, light is not emitted, where does the energy go? It gets redistributed in the various modes of motion of the surroundings. If it is a solution, then it gets redistributed in various kinds of motion in the solvent or in whatever medium it might be. Okay. So, now if you keep the light on, then what happens? You can think like this, you turn the switch on, there is no molecule in the excited state population is 0. Okay. If you have kept the light on for some time, upward transition, absorption is taking place, but downward transition has also started. In this scenario, what is the population of the excited state? I mean, I do not know what the population of the excited state is, but does the population of the excited state remain the same or does it change? In the initial period, population of excited state is 0. So, when the light is switched on, the population increases for some time, right, and then what happens is it starts getting depopulated as well. So, eventually what happens is this rate of excitation and rate of de-excitation, they become equal. So, in that state, in that situation, dpx where Pex is the population of the excited state, dt is equal to 0. Okay. This, when this condition is satisfied, then we say that a steady state has been achieved. Have you encountered the term steady state sometime again in class 11 or maybe first year college? Chemical kinetics, we use a steady state approximation for what? If you have a reaction like reactant goes to intermediate, intermediate forms product, then we say that after an initial induction period, population of the intermediate does not change. So, you get this kind of an equation there. That is called steady state approximation. Okay. I will not allow myself to digress and talk more about steady state approximation, that is a favorite topic. But so that is what happens when you shine a molecule with light as well. If you keep the light on, then after a very short time, and very short time means maybe picosecond or something, steady state is achieved. All right. Now, if you record an absorption spectrum or an emission spectrum, provided the sample does not degrade, the spectrum will not change. All right. Okay. So, the question is, what is the meaning of a spectrum? I just used the term spectrum. What is a spectrum? Range of wavelengths. But in English language, a spectrum means a varied collection, right? A spectrum of events or something like that. But to spectroscopists, a spectrum is a plot where y-axis is intensity or some measure of intensity, and x-axis is energy or some measure of energy. Okay? It can be energy, it can be wave number, it can be frequency, it can be wavelength, something like that. Okay? So, if I draw some kind of a spectrum, absorption or emission, under steady state, provided your sample is stable, the spectrum does not change. Okay? And of course, you can do two things. You can focus on this and try to record absorption spectrum, or you can focus on this, try to record emission spectrum. So, before we go on to the actual measurement, what we would like to learn is how do you, what is it that you measure, and how does, say, intensity depend on various factors. So, we start with something that many of us might actually know. We will start with Lambert-Beer's law. What is Lambert-Beer's law? Yeah? Yeah, equal to epsilon CL. I just write absorbance, this is called absorbance, right, not absorption, and I will write its expression log of, what is it? I0 by IT. So, let us say this here is your sample, light with intensity I0 falls on it, and the intensity of light that goes out or is transmitted is IT. So, IT is usually less than I0. So, what is I0 minus IT? Where is that intensity gone? It must have been absorbed, or it might have been reflected. So, for now we talk about samples that absorb and do not reflect. So, then for those I0 minus IT will be equal to I_abs, right. So, this is something that we are going to need in a minute. So, see, if I want to measure absorbance, I need to know I0 as well as IT. So, I must have a way of measuring both, and in the next module actually we will go to the lab and we are going to see how an absorption spectrum is actually recorded, and one of you is going to record it, and then we will see it with our own eyes. But let us not forget that we need to know I0 as well as IT. We are going to draw the schematic very soon. So, this is the important thing for absorption spectroscopy. Now, before we leave this, tell me what is the unit of C here? Mole per liter, molar. What is the unit of L? Length. This is L, right? Length of the sample through which the light goes. That is in centimeter, and C is in mole per liter. What is the unit of absorbance? There is no unit. Please remember, absorbance does not have a unit. Sometimes in literature we see absorbance written in arbitrary units, it is wrong. The unit is not there, so its arbitrariness, the question does not arise. You can have normalized absorbance. Sometimes you want to make all the spectra of the same size, that is a different issue. Then you write normalized absorbance. Okay. So then what is the unit of epsilon? Yeah? Liter per mole per centimeter. And what is epsilon called? Well, I used to call it molar extinction coefficient, but then about 5 years ago I had a student who told me that this extinction coefficient is apparently outdated and we must call it molar absorption coefficient. I actually like the term extinction because it tells you how the light slowly gets extinct as it passes through the sample, but then if it is outdated, it is outdated, what can you do? But I think everybody understands the meaning of molar extinction coefficient. So, now let me ask another thing, again going back to something that we learned at the beginning of thermodynamics. We all know what extrinsic and intrinsic quantities are, right? So, in this expression for absorbance, can you tell me which quantities are extrinsic, which quantities are intrinsic? Absorbance itself is extrinsic, no doubt about that. L is extrinsic, concentration you can change. Well, for a given solution concentration is intrinsic, but for the substance, if I think of the substance, no matter what the concentration is, no matter what the length of sample is, epsilon is an intrinsic quantity. Okay. So, what is epsilon? What does it tell us about? What does epsilon tell us about? We are talking about two states, and absorption is an upward transition between the two states, and what we are saying is that it does not depend on the number of molecules. Okay. Epsilon gives us an idea about the probability of transition. In fact, it is proportional to the square of what is called transition moment integral. Transition moment integral is the probability of transition, a measure of probability of transition that we calculate using time dependent perturbation theory. Epsilon is something that we get experimentally. Okay. They are related. We are not going to deal upon this further. Whoever is interested to know more about this, you can go through our lectures in the NPTEL course on molecular spectroscopy. All right. So, so much for absorption. The take home message from the point of view of spectroscopists, what are the take home messages? First of all, absorbance has no unit, epsilon does have a unit, and if you are to record absorbance, you must know I0 as well as I, and that is what determines what kind of instrument we have to use to measure absorbance. All right. And before leaving this topic, one more question. What are the things that epsilon depend upon? Epsilon is probability of transition. So, of course, it depends on which two states it is, right. So, if you take if you are thinking of a so DD, everybody knows, right, DD for transition is Laporte forbidden. So, if you are talking about transition between two d orbitals, of course, epsilon is going to be small. If you are talking about n pi star transition, if you are talking about pi pi star transition, in which will epsilon be larger? Pi pi star, right? N pi star transition is actually forbidden, right? Once again, for more discussion of this, please refer to our molecular spectroscopy lectures that are available on NPTEL and YouTube. So, that is first thing, which states are involved. experimentally. Well, actually this is what it leads to. Does it depend on concentration, epsilon? Usually no. Well, actually no. But does it depend on wavelength? Yes, otherwise your spectrum would not be a spectrum, it would have been flat. Of course, it depends on wavelength, and wavelength dependency sort of comes from the what we have stated already, that it depends on which levels are involved in the transition, okay, transition moment integral. Does it depend on temperature? Not unless one of these states get populated by change in temperature, otherwise it is not an activated process. Generally only activated processes depend on temperature, but here it may be that we are talking about transition from one state to another one, and one of the states is not formed at a particular temperature, then it might, but that is not something that usually happens, okay. So that is what it is. Now let us remember this, and let us also remember this I0 minus IT is equal to IABS for a non-reflecting sample. Let us do a quick discussion on emission. We will talk about electronic states later. Let us say that once again we go back to those levels, and there whatever, I am not saying they are electronic levels, some level. So you have populated the excited state, and now it comes down. We will draw the same picture once again, okay. So you have some intensity of emission, right, and we have already discussed intensity of the light that is absorbed, right, that is I0 minus IT. So now see what kind of intensity I will get depends on two things. First is once again what is the probability of downward transition between these two levels, right. So if you go back to Einstein's treatment, which we are going to do a few classes later, here we are talking about spontaneous emission. So that would depend on something called Einstein's A coefficient. What else? Suppose the intensity of absorption is very high. Will that affect the intensity of emission? Intensity of absorption, what is the definition of intensity? Number of photons per unit area per second per unit time, right. So if that is high for absorption, that means what? What do photons do? They promote molecules to the higher state, right. So if I bombard the molecule with more number of photons per unit area per second, then naturally the excited state will be formed to a greater extent, and if the excited state is formed to a greater extent, it is not very difficult to understand that IEM should be proportional to the population of the excited state, and population of the excited state depends on IABS. So IEM also depends on IABS. So I can write it like this: IEM by IABS is a constant. Since we are doing a generalized discussion here, we will call it phi EM, and for now we will just write emission quantum yield. Right? Does anybody want to say anything about this quantity emission quantum yield? Is it related to something that we have discussed already? Yes. So what is that? What have we said about intrinsic property? And for emission, what is the quantity that we mentioned a few minutes ago, which determines the intrinsic probability of transition? Einstein A coefficient, isn't it? So this quantum yield, you can say, is actually this Einstein A coefficient, okay, right. So now suppose I experimentally want to determine quantum yield. What will I do? Is it enough if I record the emission spectrum, or do I need the absorption spectrum as well? Remember, it is not so easy to get absolute values of intensity from these experiments. You only get relative values. And even if you get absolute values, is it enough to record the emission spectrum if I want the quantum yield, or do I need to measure absorption spectrum as well? Both are required because quantum yield is IEM by IABS. I need to know IABS as well. Okay. And remember something we said, IABS, what is it? I0 minus IT. Okay. So, that is what will come in here, I0 minus IT. Now, what would be the relationship between say IABS and your absorbance? Will there be some relationship? A is equal to log of I0 by, instead of IT, I will now write I0 minus IABS, right. So, it is not very difficult to see, I hope, that a rearrangement of this can let me actually get rid of, well, so I have already got rid of IT. What happens if I rearrange this? Log, right. So, I will write 10 to the power minus A on the left hand side. What will the right hand side be? I0 minus IABS divided by I0. So, that turns out to be 1 minus IABS minus I0. I can perhaps get rid of all this now. So, now IABS, if I make that the subject of formula, what do I get? 1 minus 10 to the power minus A multiplied by I0, right. So, in this expression I can write phi EM is equal to IEM divided by I0 1 minus 10 to the power minus A. Well, there is one factor that we have not written here. It becomes important in solution sometimes, and that factor is your refractive index, but generally the error induced by it is not so much, but it is important to know this 10 to the power minus A. Okay. This is what phi EM is, right. So, we have all the working formulae, we know what we need to record. We know that if you want to measure absorbance, then it is important that I know not only IT, but also the transmitted intensity of the transmitted light, but also I0, the intensity of the incident light. So, I should have some way of measuring both, and we now know what emission quantum yield is, and we learned that in order to determine emission quantum yield, it is not enough to do an emission experiment only, you must perform an absorption experiment as well. In fact, you must perform the absorption experiment first. So, the right sequence of doing things is record absorption spectrum first and then record the emission spectrum. Many times we see that students who want to work on emission spectroscopy just record an emission spectrum. It is not enough if you are going to talk about emission quantum yield. So, always it is a good practice to record an absorption spectrum first, then record an emission spectrum. Then you record something called an excitation spectrum, but we will come to that in the next module. So, in the next module, let us discuss a rudimentary structure of the instruments that are required to record absorption and emission spectra. They are called absorption and emission respectively spectrophotometer. That is what we will do in the next module, and then we are going to go to the lab and we will have a look at an actual absorption spectrophotometer and actual emission spectrophotometer.